paint things, make things, change things.
Hey everyone, in this video I'm going to open up a circuit I've already used here on the channel and walk you through block by block how each part of it works. I don't just want to say connect this here, I want you to actually understand why every component is where it is. Let's start with the power supply. This circuit doesn't use a transformer. It uses a capacitor, C1, at 2.2 microfarads wired in series directly with the mains. This is what's called a capacitive power supply or capacitive dropper. The idea is simple. A capacitor in AC offers an opposition to current flow called capacitive reactance. The formula is Xc equals 1 divided by 2 pi times frequency times capacitance. The higher the frequency or the capacitance, the lower that opposition. The clever part here is that this opposition isn't a real resistance. It doesn't dissipate energy as heat, at least in theory. Voltage and current end up 90 degrees out of phase, so the capacitor limits current without heating up, unlike a resistor doing the same job. That's why this topology is so common in low-power circuits: cheap, simple, and no bulky transformer. After C1, the AC reaches a bridge rectifier, B1, a DBL207G. Its job is to turn alternating current into pulsating direct current. Look at the input sine wave. It rises, falls, crosses zero, flips polarity, a typical 60 Hz wave. The bridge uses its 4 diodes to make use of both half cycles, positive and negative, flipping the negative half cycle upward. The result at the output is a sequence of humps, always positive, never crossing zero, and at twice the original frequency, 120 Hz. That frequency doubling is exactly why the filter capacitors that come next can get away with less capacitance than they'd need with half-wave rectification. This little resistor here, U$2 at 100 ohms, sits in series in the mains return, ahead of the bridge. Its job is very different from the capacitors. When you plug the circuit in, capacitor C1 is still uncharged at that instant. It behaves almost like a short circuit. If nothing were limiting it, the only thing holding back the current would be the parasitic resistance of the wires and diodes, and that can produce a current spike of tens of amps just for a fraction of a cycle. That stresses the bridge rectifier and can even damage plug or relay contacts. With U$2 at 100 ohms in series, that worst case drops to around 1.4 amps, an order of magnitude safer. The price you pay is that, in steady state, it continuously dissipates a small fraction of a watt. Not much, but unlike the capacitor, it really does get warm. After the bridge, we have 2 electrolytic capacitors, C2 at 100 microfarads and C3 at 470 microfarads, both in parallel on the same rail, along with a 5-volt Zener, ZN2. On their own, these capacitors would leave a fairly large ripple, on the order of a volt or so, shaped like a sawtooth, charging quickly with every pulse from the bridge and slowly discharging in between. But the Zener, ZN2, actively shunts the excess current to ground, clamping that voltage down to something close to a flat line at 6 volts, with only a residual ripple of a few tens of millivolts. In other words, the capacitors do the filtering, but the Zener is what actually regulates and stabilizes the rail. C3, sitting closer to the logic chips, also acts as a local charge reserve for the fast current spikes that CMOS logic pulls when it switches. Now we get to the sensing side. The infrared emitter LED isn't even drawn in this schematic. Only the J1 connector is, because the actual LED lives off-board, mounted for optical alignment with the receiver. R2 at 100 ohms closes the loop for that LED. It sits between the emitter net and ground. Whatever current flows through the LED out there has to pass through R2 before it returns. It's the classic LED current limiting resistor. Current equals supply voltage minus the LED's forward voltage divided by the resistance. With a 5-volt supply, a forward drop of around 1.3 volts, typical for an infrared LED, and a 100-ohm resistor, the current works out to about 37 milliamps, enough for a decent mid-power emitter without blowing past the datasheet limits. On the other side, we have the receiver photodiode, which also isn't drawn. Again, just the connector, the receiver net. This photodiode is deliberately wired reverse biased. The cathode goes to 5 volts, the anode goes to the node where R3 sits at 10 kiloohms. Now, reverse bias normally means doesn't conduct, and that's exactly the behavior this circuit is exploiting. In the dark, the photodiode only lets through a leakage current in the nanoamp range, practically nothing, so the node above R3 sits close to 0 volts. But when infrared light hits the junction, it generates electron-hole pairs, and that reverse leakage jumps up into the microamp range, proportional to the light intensity. That current, flowing through R3, creates a voltage drop across it. Voltage equals the photodiode current times the resistor value. That's how infrared light becomes a voltage in this circuit, with no amplifier needed before the comparator. This node is exactly the signal that feeds the next block. The photodiode signal, already converted into a voltage by R3, goes into the non-inverting input, pin 3 of IC2, an LM741 op-amp. But here, it's not wired as an amplifier with feedback. It's running open loop, working purely as a comparator. Its inverting input, pin 2, gets an adjustable fraction of voltage from R6, a 10 kiloohm potentiometer. That pot sets the trigger level, the threshold, which you adjust physically by turning the trimmer. The behavior is simple. As long as the photodiode signal is below that threshold, the comparator's output, pin 6, stays low. The moment the signal rises to meet or cross that threshold, meaning pin 2 and pin 3 become essentially equal, the output flips high almost instantly because an op-amp's open-loop gain is enormous. That low to high transition is what, further down the line, lights up the circuit's indicator LED. The comparator's output doesn't go straight to the flip-flop. It first passes through a logic gate, IC3A, which is a quarter of a CD4093, a NAND gate, but with Schmitt trigger inputs. Notice that both inputs of this gate are tied to the same point. That's not being used as real NAND logic with two independent inputs. It's the classic trick to turn the gate into a Schmitt trigger inverter. And why does that matter? A Schmitt trigger doesn't have a single switching point. It has two thresholds, one for the rising transition, one for the falling one, forming a hysteresis band. The comparator's output can have a relatively slow or slightly noisy transition near its switching point. Without this Schmitt trigger, that slow transition could cross the threshold back and forth several times, generating multiple false clock pulses. With hysteresis, once the signal crosses the upper threshold, it can only go back once it drops well below the lower threshold. That cleans the transition into a single, fast, definitive edge, which is what feeds the flip-flop's clock. That clean pulse goes into pin 3, the clock, of IC1A, a D-type flip-flop inside a CD4013. A normal D flip-flop just copies whatever's on the D input over to Q on every clock edge. But notice something interesting in this schematic. Instead of coming from somewhere else, the D input is fed by the flip-flop's own inverted output, Q bar. That means, right before every clock edge, D is always holding the opposite of whatever Q currently is. So when the clock edge arrives, Q copies D, but D was already the inverse of the previous Q. The result? Q flips to the opposite of what it was. It toggles. This is the classic trick for turning an ordinary D flip-flop into a toggle, or T flip-flop, without needing a dedicated chip for it. In practice, every time the infrared beam gets interrupted, generating one clock pulse, the output flips state, turns on if it was off, turns off if it was on. And now we reach the last block, the power stage, which is basically a homemade solid-state relay in 2 steps. First step, R1 at 330 ohms limits the current through the LED that lives inside OK1, a MOC3020. But this isn't a regular optocoupler with a phototransistor output. It has a tiny TRIAC on the output side. When the internal LED lights up, it optically fires that little TRIAC, with no electrical connection at all between the logic side and the main side. That's the circuit's galvanic isolation barrier. One important technical detail. The MOC3020 is a random phase type. It has no built-in zero crossing detection. That means it can fire at any point along the sine wave, not just right at the zero crossing. It's simpler and cheaper, but it generates a bit more electrical noise at the moment of switching. Second step, when the MOC3020's internal triac fires, it lets a pulse of current through R5 at 360 ohms straight into the gate of U$1, a BT136. This is the real power triac, sized to handle the actual current of whatever load is connected at JP2. Once triggered, the triac latches on, conducting until the current naturally drops to zero at the end of that half cycle, and then it waits for the next gate pulse to fire again. And that's it. From the capacitor that replaces a transformer, through the infrared sensor, the comparator, the digital logic, all the way to the triac that actually switches the load on and off. If anything about a specific block wasn't clear, drop a comment and I'll answer. Subscribe to the channel and see you in the next video.